So today is Tuesday, 3/19, and we just had some time to check homework 6-4. Before the end of the hour, I'm going to try to give you your review sheet and your homework sheet for this chapter. I feel like I have those ready. And then we'll work on notes for 6-5. We'll still be working on those on Wednesday and Thursday, possibly. And then have review time on Friday, exam part 1 on Monday, exam part 2 on Tuesday. So this is the trigonometric form of a complex number, and we have all of the tools that we need to find the trigonometric form of a complex number. Just give me a head nod. Have you graphed complex numbers on a coordinate plane before? Okay, and maybe not. I just remember somebody asking me recently a question about this. Um, not in any class that I teach, but we're very familiar with the x and y axis, and we know that this point, we'll say it's 2 comma 1, means it has an x coordinate of 2 and a y coordinate of 1. Well, when we do the complex plane, we then have a real axis, an imaginary axis, imaginary axis. And so if I have that point that is 2, 1, now that means the real part of the number is 2 and the imaginary part is 1. So if I wanted to write that as a complex number, it would be 2 plus, I'll say 1i. We don't usually say 1i, but just to make sure that I kind of am showing that. And then these are a plus bi, which is the complex form of a number. So that is just the basic idea behind a complex plane, and we'll see that as we go through these first couple of slides here. And so trigonometric form of a complex number, we want to plot complex numbers in a complex plane and find absolute values of complex numbers. You'll find that's going to be pretty straightforward, the Pythagorean theorem. Write trigonometric forms of complex numbers, multiply and divide complex numbers written in trigonometric forms, and we'll use de Moivre's theorem to find powers of complex numbers. And you're going to like de Moivre's theorem, I would think, because it allows you to not have to do a bunch of foiling out, multiplying binomials as we go. And then find the nth root of complex numbers. So the first thing we'll look at is the complex plane. And I just talked about it. A question? Yes, he talked a little bit about that, and in the Pascal's triangle. I don't know, did he say that word or yeah? And yes, Professor Ouija kind of talked a little bit about that, and it's along those lines, not quite at that, but we will cover that hopefully before the end of the year as well. And so complex numbers, and you've maybe experienced them before. I is equal to the square root of -1. And everybody's good with that, I'm hoping, right? And I is the square root of -1. And so when we have a complex number, a plus bi, we can just kind of look at it there. And then when we put it on this complex plane, and then really it's just exactly what I said a few minutes ago. When we plot this point, they plotted 3, 1, which is 3 plus I, and -2, -1, which is -2 minus I. So the real axis is the horizontal axis. The imaginary axis is the vertical axis. And then the word absolute value, um, might throw you off, I guess is the way I'd say that. But the absolute value essentially is going to be the distance from the origin out to that point. And just like absolute value is always positive, and absolute value is is considered a distance. So the Here we go. The definition of the absolute value of a complex number, you'll want to know that, but it's if we consider z to be a plus bi, then the absolute value of z, the absolute value of z is just the absolute value of a plus bi, which is the square root of a squared plus b squared. The I is not actually, in a part of that calculation. It's truly the distance from the origin to that point AB on the coordinate plane. So you do ignore I in that moment. Just kind of keep that in mind. And so then if it's a real number, then the absolute value will be the absolute value of that real number, correct? Because you're going to, the zero or the imaginary part would be zero. You're going to square that number and then square root it. So it will be positive answer, or the absolute value of A. So it does kind of follow our rules as we go. But we use that Pythagorean theorem concept a lot in all the things that we're doing. So then, just to be able to plot and find the absolute value of a number, so -2, 1, 2, 5, 1, 2, 3, 4, 5. So if this is a complex plane, then this point z, which is at -2, 5, and this is the real axis, and this is the imaginary axis. And then that point, -2, 5 stands for that z, which is -2 plus 5i. The absolute value of z then is just the square root of -2 squared plus 5 squared, square root of 4 plus 25, square root of 29. So the absolute value of z is the square root of 29. So far, so good. Yes, no? Just finding those. Now, the next thing we want to do, and I'm not going to use this point just because it's over in that quadrant. It's easiest kind of to think about something in a first quadrant. But think a moment about having a point out here, and I'll just draw a picture of a right triangle. We know that this is theta, x, y, and r, correct? Remember that from just previous work that we've done. And so really, I can have that point there, and I kind of intentionally made it not at a grid point, but I can have a point anywhere, really. Correct? I can have a point anywhere, and I can think of it as having x and y coordinates, or real and imaginary coordinates, but I can also kind of think of it in terms of the angle and the radius. So do you agree that the sine of theta is y over r, correct? And so really, I'm going to go to a different picture. I'm going to rewrite this picture maybe at the next heading. Here it is. So this is really, now we want the trigonometric form of this complex number. So this is still the real and the imaginary axes. And here's my xy. Actually, I'll call them AB because that might be a little easier to follow for what we're doing. Ooh. And maybe I'm going to go back to x and y. This is our x value, our y value, and our r value. So if I wanted the sine of theta, it's y over r. Sine theta is y over r. And so y is r sine theta. Do you agree with that? And we've kind of said that before. And then cosine theta is x over r. So x equals, or r cosine theta is equal to x. And so what that really means is we can say that this a and b which are right there, can be replaced with r cosine theta and r sine theta. So if I write that as a complex number, what is it? A plus bi, correct? Yes, a plus bi. So if I write this as a complex number, it's going to be r cosine theta plus what? Yeah, r sine theta I. And so, like, the reason I pause there is where are you going to put that I? I'm going to put it at the end, but how should I put it if I'm going to put it at the end? Well, yeah, because if I go r sine theta I, what's wrong with that? It would be theta I, right? And so it's r sine theta times I. So just something to be uh, aware of as we go through. So this is the trigonometric form. I don't know if Professor Ouija talked about it when he was here the last time, but generally he talks about it on that day he's here, but usually he has that little computer program to go over. And that is, he always likes to ask if we've done polar coordinates. And so these are called polar coordinates as we go through. And that is what we'll be looking at right now. And so sometimes they put the r cosine theta in parentheses as well. And we haven't had this yet, but the A part and the B part of A plus BI as we look at that. So now we'll go through a couple of things. And we know how to add, subtract, multiply, and divide complex numbers. And so when you think about that angle, there is something to kind of think about there. And this is just going through what we just said. A is r cosine theta, B is r sine theta. R is that radius of the circle, correct? So we're kind of used to that. And then here is the trigonometric form of a complex number. So this side is the trigonometric form of that complex number. R cosine theta plus r sine theta I. And you are going to want to know that. Some things just, some things to kind of say about those, and this next slide kind of goes over some more things. So the trigonometric form of a complex number, if z is a plus bi, then z is also r parentheses cosine theta plus I sine theta. So what did they do to write it now? They pulled out the r, and also do you notice they moved strategically the I to in front of sine theta? You know what I mean? That just makes us all a little happier as we go. And so this is a very, this is the trigonometric form of a complex number. And where a is r cosine theta, if we distribute that out, and b is r sine theta, r is the square root of a squared plus b squared. Now, the tangent of theta is b over a, but do you agree that that tangent of theta that's b over a is going to give us a reference angle? You with me on that? Remember how we've done that before, and really we did b over a, in a different situation, but it works out to be that same thing. And then r is just called the modulus. R is the modulus. And theta is the argument. And those aren't used in like general talking a lot of times, but they are the mathematical names of this. And the trigonometric form of a complex number is called the polar form. So when somebody says, oh, do you know how to do something in polar coordinates? Well, that's what they're talking about, is just writing it instead of in this complex form in terms of the radius and the angle. that is made. And generally, so just a note to self, you're going to think of that as the reference angle, just to let you know. And then you're going to do like, the all students take calculus to figure out the actual angle. Generally, that angle could be an infinite value, correct? Because of the spinning, backwards or forwards. Generally, though, we go from 0 to 2 pi. Generally, we don't use negatives, except sometimes they creep in like here. You know what I mean? Because that's just it's easy to say that it's just that little negative instead of going all the way around that way. So, there are some things that we just, um, that are sometimes used as we go. Because there are an infinite number of choices, a trigonometric form of a complex number is not unique. And then here it says, normally theta is restricted to that interval from 0 to 2 pi, although occasionally it's convenient to go with a negative angle that we just talked about. And so then probably, let's see. Oh, here we go. Let's just find some things, write some complex numbers in trigonometric form. So we want to be able to go back and forth. So here is our number. Z equals -2 minus 2 the square root of 3i. And I tried to hike that I out a little bit because it is not under the radical. I mean, I can't even imagine a time when that I is supposed to be under the radical, in any problem we'll ever do. So just know that it should be out there. In my heart, I like to write it 2i, the square root of 3, but for now, I'll just put it like that. My other note to self is, you know what a coordinate axis looks like. So think about either plotting these points or just, thinking about what quadrant they're in. We don't really care the exact location, but we do care about what quadrant they're in, and that'll help you figure out the angle. So the angle dynamic. So do you agree that if this is negative and a negative, it's in this quadrant, correct? We don't really care that much exactly where it is, but then that'll help us get that angle theta. When we get the reference angle, then we'll know that we have to go kind of all the way around there. Just as a note to self as we go. So we need to find the complex form, so we need to figure out what r, and theta are. So we have to figure out what r is, and we have to figure out what theta is. So how are we going to figure out r? Say it again. Okay, so -2 squared really, plus -2 square root of 3 squared, and we need the square root of that. So that's going to be r. So -2 squared is 4. What is the square root of -2 the square root of 3 squared? Anybody? Well, what's -2 squared? 4. What's the square root of 3 squared? Just 3. So what's 4 times 3? It's 12, and it's got to be positive, yep. And so it's 12. So this will be 4. That just is plain old 3. And so 4 times 3 is 12. And so r in this case is the square root of 16, right? Which is just 4. So that's kind of nice. It turns out to be a whole number. How are you going to get theta? What trig function do we use? Tangent. And so I like to think of it, and so really I remove these negatives. I use the absolute value of b over a. So I want to find the reference angle, the tangent of that reference angle. Tangent of the angle, I'll just kind of put a little angle symbol there, is b over a, so 2 the square root of 3 over 2. And, I could use them negative, that's fine, because it'll turn into a positive. And so the tangent of my reference angle is the square root of 3. Well, on our chart, when is the tangent equal to the square root of 3? What's that? And we give those in radians. Any thoughts on where that is? I feel like it's over there. Yep, it's at pi over 3. So just a little reminder, here's sine, cosine, tangent. When you get out here, 0, 1/2, square root of 2 over 2. Here's square root of 3 over 2. Here's 1/2. And so this is the square root of 3, and that's at pi over 3 right there. And so our reference angle is pi over 3. We just said it is, you are going to have that clue all the time that, it's a negative and a negative, so it's in this quadrant. And so our reference angle is pi over 3. So what's our actual angle theta? I have to go I have to go pi plus pi over 3. So 4 pi over 3. So I'll just write up pi plus pi over 3. So 3 pi over 3 plus pi over 3 is 4 pi over 3. So now I found r and theta, but now I still have to write it in complex form. So how do you write the answer then? Z equals, because it's still z, what does z equal? R cosine theta plus I sine theta. So then go ahead and put those in for me. Oh, yes, I didn't. I started a 4 and changed it into a pi. So sine 4 pi over 3. So those, and notice, they appear to be positive, but we know when we take sine and cosine in that third quadrant, those will be negative values. So, that can kind of help us. And so really, these are exactly the same thing. Do you agree with that? That and that have the exact same value. So you can check if you wrote this correctly because you can find the cosine of 4 pi over 3 and multiply it by 4 and it should be negative 2. And you can find the sine of 4 pi over 3 and multiply it by 4 and it should be negative 2, the square root of 3. So that is putting that in complex form. And so this is complex form, so I better write this down because I will tell you on the test, that you want to know the difference between what it's asking you to give as an answer. So this is the complex form of a complex number, and this is called the standard form. Standard form. So if I had the complex form, could I get the standard form? Could you, if you had the complex form, could you get the standard form, do you think? Do you think you could? Well, you're just going to find what the cosine of that is, you're going to find what the sine of that is, and you're going to distribute the r. Does that make sense? But r is not always going to be like a whole number. In this case it is, but let me go to this. And so this is a complex number in trigonometric form. And so, oh, wait, just a minute. I just want to see what I wrote there. Oh, complex number. Oh, I wrote this wrong. Complex number in trigonometric form. In trigonometric form. Oh, I'm glad I somehow in my head I was just standard form a plus bi, trigonometric form r cosine theta plus I sine theta. So I'm glad that I remembered to do that. So this is z, which is in trigonometric form, square root of 8 times cosine negative pi over 3 plus I sine negative pi over 3. By the way, do you agree that that theta has to be the same in a particular number, correct? And so we want to write it in standard form, a plus bi. So we have to find the cosine of each of these and sine, and maybe we'll clean that square root of 8 up. Why do I say clean that square root of 8 up? Yeah, this is 2 to the square root of 2. Yeah. So the first thing I would do is maybe just kind of think about negative pi over 3. So all students take calculus, and that's going to be down here, correct? There's my angle. And so my reference angle is just plain old pi over 3, right? And cosine will be positive, sine will be negative. The cosine of negative pi over 3 is equal to the cosine of pi over 3 because it's positive. And what is the cosine of pi over 3? 1/2. And then the sine of negative pi over 3 is going to equal, well, since sine is in that quadrant negative, it'll be the negative sine of pi over 3. And what's the sine of pi over 3? Square root of 3 over 2. Yeah, if one's half, the other one's square root of 3 over 2. And oops, I didn't throw in my negative. And then I would just say that the square root of 8, we kind of already talked about that a little bit. I'll just write it over here. Square root of 8, square root of 4 times 2, square root of 2 to the square root of 2. And so z is equal to 2 the square root of 2 times the cosine, which is 1/2, plus, my plus doesn't look very good up there, plus I times negative square root of 3 over 2. And yeah, I think I have the right amount of parentheses there. And then I want that to be in a plus bi form, right? So when I distribute that, what's going to happen? What am I going to get? What am I going to get? Square root of 2. And minus, correct? And what's that other part going to be? Square root of 6. So the 2's are going to cancel in that part, and square root of 2 times square root of 3 is just square root of 6. So square root of 6i, you know, I like to write, personally, I the square root of 6. If you truly, the answer is square root of 2 minus square root of 6i. And you know, I try to put that I out there a little bit as we go. Now, I want to remind you of some things that you've done before. Let me. Here's my little. I'm going to remind you of some things we've done before. And maybe I'll remind you of those right away. So, cosine of alpha plus beta. Do you remember that formula? Anybody remember it like off the top of their head? Cosine alpha plus beta is, yep, it's a sum one. Uh, it's, no, this is cosine, so it's the two names together at the same time, but it's cosine alpha, cosine beta minus, and then what? Sine alpha, sine beta. Okay, and then while we're at it, what's the sine of alpha plus beta? Because that's maybe the one you were thinking of. Sine alpha plus beta is what? Sine alpha cosine beta plus, yeah, I'll write it cosine alpha sine beta. But yeah, either way is fine. Okay, so do you recognize those? Because we're going to experience those in a few minutes. Now, I just said, you know, we don't have to FOIL a lot of things out, but in this case, we're going to kind of see what the answer is, and then we're going to look for a pattern. So if Z1 is R1 cosine theta 1, plus I sine theta 1, and Z2 is R2 cosine theta 2 plus I sine theta 2. I'm going to multiply those together, okay? And I think it's good for us to experience that. So that means we're going to take R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. So what do you think I should do? I have to FOIL something out, but I personally would move this. Where do you think I would move it? To the front. So do you agree that I could just say, oh, it's going to be R1 times R2 and then times those two things in parentheses, correct? So R1, R2 equals, and then it's going to be cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. And so in your mind, a couple things to think about. Like the alpha and beta a minute ago, they're like theta 1 and theta 2, possibly, you know, when we look at that. And then this is a complex number, so at the end we're going to have I squared. Do you agree? And what's I squared? Negative 1. So we'll just, you know, just kind of keep that in mind. So R1, R2. When I multiply that, it's going to be cosine theta 1, cosine theta 2, right? I think I'll leave it like this. Cosine theta 1, cosine theta 2. I'll multiply this one plus I sine, or I cosine theta 1. We'll say cosine theta 1, sine theta 2. And then this one will be plus I sine theta 1 cosine theta 2. And then the last one is going to be what? Plus I squared sine theta 1 sine theta 2. Do you agree? Okay, so I want to match these together. I want to match that one and this one. And I squared is what? Negative 1. So I have cosine alpha cosine beta minus sine alpha sine beta. What's that equal to? Okay, so R1, R2. This is going to be cosine theta 1 plus theta 2. Yes, I know. Yeah. And then look at this one. I have sine theta 1, cosine theta 2, and cosine plus cosine theta 1, sine theta 2 with the I in front, plus I. And then this is, what is that? Theta 1 plus theta 2. So look at this end result. Do you want to FOIL that out every time? No. Think about if you had these two things and complex numbers, what do? You multiply the modulus and you add their arguments. Does that make sense? And that's way easier than FOILing that out every time. Don't you agree? And then whatever that product is and whatever these are, then that's your new angle. And if you had to write it in standard form, you could. So that's what we're going to write down. And then try to figure out this. We're really not going to do that, but just because our time is kind of limited. This is multiplication and division of complex numbers, and we've already gone through. Here it is. And this is what I'm leaving you with today. And you can either write it now or later, but just look at it right now. If Z1 is R1 cosine theta 1 plus I sine theta 1, Z2 is R2 cosine theta 2 plus I sine theta 2, then when you multiply those and add the angles. I did not give you your review sheet. Do you want it before you leave or do you want it tomorrow?